Hello everyone. This is a video tutorial for the Keep Talking and Nobody Explodes module called Rule of Three. This is a relatively straightforward module, although there is some heavy math involved. Well, slightly heavy math involved. But we will talk about some ways around that if you would like to avoid that, and we'll also talk through how to do the math yourself if you would like to. So first off, let's just get ourselves oriented here in the module. So as the manual says, there are three spheres colored yellow, red, and blue, floating within a 3D space along the X, Y, and Z axes. Each sphere is cycling through three different positions. So if we look at our module in the game here is one of these mods, and we can see the red, yellow, and blue things moving around. So our spheres are going various places, they're moving left and right, they're moving up and down, and also if we tilt the view sideways, they are moving forward and back, closer to the module, farther away from the module. But if you notice, and I don't believe it says this in the manual anywhere, but the three spheres are never at the same position, right? So there's always one high, medium, low. In this direction, there's always one high, medium, low at any point in time, and then there's always one left, one middle, one right at any point in time. So our goal is to decipher the meaning of these movements, track exactly what they are, use that information to do a calculation, and then submit the answer to that module. So just real quick, just to keep track of how the module does things, moving left and right as we look at the module, that is considered the x-axis, with negative to the left and positive to the right. Moving up and down as we're looking face on the module, that's the z-axis, with up being positive, down being negative, as you would expect. And then looking from the side, the up and down here, so that's moving closer to the module or farther away from the module, that is the y-axis as far as the module is concerned, with the negative part of the y-axis being closer to the mod and the positive part being farther out. For the physicists watching, that does mean this is a left-handed axis system that the module is using. I apologize, it's not my fault. So, first thing we need to do here is just write down what all of these spheres are doing at each step in the process. And one thing to keep in mind is that we see three movements, and then the spheres pause for a second to tell you where the movements start and stop. The position they are where they're pausing, that's the third movement. That one counts as the third movement. So where they start up again after the pause, that's the first movement. So if we just look, say, in the X direction right now, the red sphere moves to the middle, stays in the middle, and then moves back to the right. So I'm just going to write down that the red's X movement is middle, middle, right. The Z movement for red, that's moving up and down as we look at the module this way. That's middle, up, down. So I'll write that down as middle, up, down. Whoops, in the Z axis, middle, up, down. And if we look from the side, here's the pause. Red is middle, down, middle. Right, so we see it's middle, then very close to the module, then back in the middle of the three. So that was middle, down, middle. And then we just need to track this for all three of the spheres. So here we go. Yellow is going to go left, left, middle. And then top, down, middle. So up, down, middle. And then again, looking from the side, you see yellow is the highest sphere up all the time. So that's just going to be up, up, up. And then we just have to track blue. But now, if we look at what we said before, I don't even need to read the blue, because I can just figure out if X is on the left and, or sorry, if yellow is on the left and red is in the middle at the very beginning, that means blue has to be on the right in this first movement. And we see there, blue is right, right, and then left. Now, it's probably easier to just have your diffuser read that to you, or if you're looking at it on Twitch Plays, just look at it yourself. But so we can see that blue is right, right, left, and it is bottom, middle, top. So down, middle, up, the way I've been writing these. And then from the side, we're going to see that blue is down, middle, down. So we'll write that down, down, middle, down. All right, so we have now read the movements of our 3 spheres on the module. And now we have to convert these into ternary numbers, and not just ternary numbers, but balanced ternary numbers. So I'm assuming that you are somewhat familiar with how balanced ternary works. It's basically like base 3, except instead of using 0s, 1s, and 2s to represent how many 1s and 3s and 9s and whatever you have, you instead use pluses and minuses. So you might have, if you want to represent 6 in balanced ternary, it's 9 minus 3. So that would be plus minus 0. Right? So in this case, we're going to convert every single one of these movements to a balanced ternary number. And one of the things you have to remember with this module is that it sort of does things backwards. The least significant part of that ternary number is the first cycle. And the most significant part is the third cycle. So to me, this is backwards of the way I would normally write them. So I'm going to have to flip these backwards. So I read this right at the end. That's in the positive direction in the x-axis. That's the most significant bit, so that goes first. And then the 2 middles, those represent 0s. Those go second and third. Now, for the y-coordinate, this is the same either way. So 0 minus 0, because again, middle represents the 0, down represents the minus 1, and the other middle represents the 0. And then down, up, minus, we go minus, plus, 0. All right, now in the y direction, or sorry, this is the yellow sphere. Y and yellow confuse me very often on this one, but that's all right. So this is 0 minus minus. Again, reading middle, left, left, sort of reading that backwards. Our u is plus, plus, plus. And then the z-axis is 0 minus plus. And then lastly, for the blue sphere, this will be minus, plus, plus. Again, left is in the negative x direction, right is in the positive x direction, and we flip those. Down, middle, down, and then up, middle, down. So now we have a balanced ternary number for each one of these 3 spheres and each one of the 3 axes. And so we just convert those into their ternary equivalent. So again, this plus 0, 0, this represents plus 9. And then this would normally be the 3's place and the 1's place, but we don't have any 3's or 1's. So those become plus 0, plus 0. So that total is just 9. And then similarly here, 0 minus 0, that's 0 9's, a negative 3, and then 0 1's, so that's a total of minus 3. And minus plus 0, that's a minus 9, from the minus in the third bit. A plus 3, from the plus in the middle, 0 1's, and so that's a total of minus 6. And so I'll run through the rest of these pretty quickly. So minus 4, plus 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 is 13, 0 minus plus is negative 2, and then minus plus plus gives us minus 5, minus 0 minus is minus 10, and plus 0 minus is 8. And so then each one of these sets of 3 numbers, 9, negative 3, negative 6, that gives us a set of 3 coordinates. Right, so the number that came from the movements in the x-axis for the red sphere, that 9, that becomes the x-coordinate of our first point, the point corresponding to the red sphere. So that point is 9 minus 3 minus 6. The point for the yellow sphere is minus 4, 13, minus 2. And then lastly, for the blue sphere, we have minus 5, minus 10, 8. So one other convenient thing that you can use to check your work at this point is if that thing holds true, that none of the spheres are ever in a line with each other, right? They're never two at the same point to the left or to the right or anything like that. If we look at our, sorry, didn't scroll down far enough there. Lost track of where I was writing down these coordinates here. But we see the blue coordinate, for example, is -5, -10, 8, just from the numbers we calculated from the blue movements up here. But as I was saying, since there are an equal number of pluses and minuses and zeros in each position, if we look at the x-coordinates of the three spheres, they should add up to 0. 9 minus 4 minus 5, that's a 0. -3 plus 13 minus 10, that's 0. -6 minus 2, 8, that's 0. That has nothing to do with solving the module, but it's a good way to check that you haven't screwed up your arithmetic so far to this point, right? So here are our three coordinates. And so at this point, we have two options for how we are supposed to actually find the solution to our module. The first option is described in the manual, right? It says, here are your coordinates, x1, y1, z1, x2, y2, z2, x3, y3, z3. And then it gives you a whole bunch of formulas to follow to calculate the area of the triangle that you would get if you connected these 3 points to each other. So if you actually did some three-dimensional geometry, connected these points, you would get a triangle. What is the area of that triangle? So you can calculate that by hand, and I will show us how to do that in just a second. But frankly, I never do that when I'm solving this module. There is a handy website called wolframalpha.com. You just go there. You can plug in all sorts of things here and ask it to calculate things for you, and it will happily do it. So one of the things it can do is find the area of this triangle. So if I just plug in my points that I have, -5, -10, 8, and I say find me the area of the triangle with those coordinates, it will find it for me. And we'll say, oh, I'm thinking about the triangle with these coordinates. Here is the area, 211.308. So it's very likely that when you do this calculation, you get some weird decimals here. We just completely ignore those. All we do is keep the 211. So that 211, that is the answer. That is what we need to submit into the module. All right. Now, unfortunately, this module only understands numbers in ternary. So we have to convert this into balanced ternary. And so there are various ways to do this. Probably the most systematic way is to first write this in ternary numbers. So you find the largest power of 3 that fits into your number. In this case, 81 is still less than 211. And in fact, 2 of 81 will fit into there. So that's 162. What's left over after that is 49. My highest power of 3 that fits in there is 27, so that's 27 plus 22. My highest power of 3 that fits in there is 9, so that's 2 9s, that's 18, plus 4, and then 4 we split apart into 3 and 1. So in regular ternary, that means we would represent 211 as 2 81s, 1 27, 2 9s, 1 3, 1 1. But now here's the problem. We have to write this in balanced ternary. So really, this 162, we don't want to write as 2 81s. In balanced ternary, that's really 243 minus 81. So in balanced ternary, basically what happens is this 2 turns into a plus minus. All right, so this 1 2 1 1 I'm just leaving alone right now, but this 2 that would represent 2 times 81 in normal ternary really represents 243 minus 81 in balanced ternary. All right. So then this 1 is perfectly fine. That just converts into a plus 1. But now this 2, we once again have to convert this into a plus minus. So we get minus one of those. We get another one of these. Now we have 2 of these. Oh, but that's bad. Balanced ternary doesn't like 2 things. So we've got to convert that into a plus here and a minus here. And so now we're in good shape because the plus here is going to cancel with the minus there. That becomes a 0. and a minus there, and then these two become pluses. So if we double check what we've just done here, this is the 243 place, 81, 27, 931. So this represents 243 minus 27 minus 9 plus 3 plus 1. And if we check, that really does equal 211. So this is our answer. In balanced ternary, as the module will understand, plus 0 minus minus plus plus. And now one last time, we have to notice for ourselves that this module does everything backwards. So we have to enter this starting from the least significant bit. So we really enter this as plus plus minus minus 0 plus. And then if we just look back at the manual here, it's very straightforward. Plus is blue, 0 is yellow, and red is -1, a minus. So this plus plus minus minus 0 plus is really blue, blue, red, red, yellow, blue. So that is what we have to input into the module to solve it. Blue, blue, red, red, yellow, blue. And the way we enter submission mode is very easy. We just click on the any one of these three spheres, and then they'll start spinning around in a circle, and we just click on them in the order blue, blue, red, red, yellow, blue. Blue, blue, red, red, yellow, blue. You do have to click before they spin all the way down into nothingness, but normally it's only like 6 clicks, so it's not too bad. And then, ta-da, our module is solved. All right, so that was the shortcut way to do this calculation at the end of the module, find this area of whatever triangle connects up these 3 points, and that actually gives us the answer that we need to solve the module. So, if you would like to know how to do this calculation by hand, if you prefer not to use Wolfram Alpha, that's fine. So, let's go over how that's going to work. So we're going to just use the same data that we had before, these same 3 points, 9, -3, -6, etc. So we know what our answer is going to be. We know it's supposed to be 211. So the question is, can we get there doing this calculation by hand? So we're going to follow along with the way the manual suggests that you do this calculation. I have my calculator handy up here. So we will be able to do all these calculations in here if we want to. Let me just clear out what I had before. And so here's the first thing that we need to do. Following along with the manual, it says, basically choose 2 of the points, J and I, your first, second, and third points, pick any 2 of those, and subtract the corresponding coordinates from each other. So subtract the x from one minus the x from the other, the y from one minus the y from the other, the z's minus each other. So what we're going to do is we'll take just the first one minus the second one, because why not? So if we take 9 minus -4, that gives us 13. If we take -3 minus 13, that's -16. And if we take -6 minus -2, that becomes -4. So, again, physically this represents the vector between these 2 points. If you started at this point and then moved 13 in the x direction, -16 in the y direction, and -4 in the z direction, you would wind up at exactly this point here. So imagine 2 points, and this represents an arrow pointing from this point to this point in space. Similar thing we can do with our second set of points. So we'll take the yellow minus the blue over here, -4 minus -5, that becomes +1, 13 minus -10, that becomes 23, and then -2 minus 8, that becomes -10. So these are our 2 vectors, u and v. And now we get to do some magic. We get to take the cross product of 2 vectors, or the vector product, u cross v. And if you've taken physics or linear algebra recently, you might recognize this formula. If not, it's fine. We just use this formula. Not a problem. So we're going to calculate the cross product of these 2 vectors using this formula. So if we take 13, -16, -4, crossed with 1, 23, -10, let's see what that gives us. So the formula for this is sort of easy to remember once you get the hang of it. So our answer to this is going to be a vector with 3 components. The first component is u2 v3 minus v2 u3. So what that really means is the second thing in u times the third thing in v, and then minus the third thing in u times the second thing in v. Right? So negative 16 times negative 10 minus negative 4 times 23, and that all goes in the first coordinate of our answer down here. So negative 16 times negative 10, and then minus negative 4 times 23. And that's all just the first coordinate. So for the second coordinate, we sort of ignore the stuff in the middle. We take u1 and v3, multiply those together, u3 and v1, multiply those together. Unfortunately, a weird thing you have to remember here is that it sort of goes backwards of how you might expect. So we take u3 times v1, so the third one here minus the first one here, or times the first one here, rather, and then minus the first one in u times the third one in v. So that'll be negative 4 times 1 minus 13 times negative 10. As a side note, if you want to know why all of this is the right thing to do, or why there's a minus sign there, or why sometimes things are backwards, take a linear algebra class. That's my best advice. There's probably a great 3 blue 1 brown video about it somewhere. Anyway, finishing up this module, if we do u1 v2 minus v1 u2, that'll be our third coordinate. So u1 times v2 minus u2 times v1. So that will be 13 times 23 minus negative 16 times 1. So if we simplify all of that mess, that will be 160 plus 92, negative 4 plus 130, and let's see, 13 times 23, 299 plus 16. So simplifying all of that down, we will get 252, 126, 315. Now this is still not our answer, right? If you'll notice, this is not the 211 that we're looking for. But this is part of the magic of the cross product, is our answer is hiding in here somewhere. So this is the last step, is we have to find the size of this vector that we just found, or the length of this vector. Again, if it's in 3-dimensional space, we're literally measuring how long this arrow is. And the way we do that is a sort of Pythagorean theorem sort of thing. We square each of the coordinates, add them all up, and then take the square root of that. So we'll just go to the calculator here. Whoops, had the focus in the wrong spot. Go to the calculator here, take 252, square it, plus 126, square it, plus 315, square it. And that gives us 178,605. And then we take the square root of that. And we get our answer, 420. Oh. Still not quite our answer. If we look back at the module over here, finally we have to have the size of that. That's because this lovely calculation we did here actually finds the area of a parallelogram, and the triangle that we want is exactly half of that. So the length of that vector is 422 point some stuff. If we then divide that by 2, finally we get down to 211.308, and dropping the decimal points would get us to the 211 that we entered before as the answer to the module. And in fact, if we look back at our Wolfram Alpha cheaty way of doing things, there's the same number, 211.308, gotten to with a lot less work on our part. But there you go. That is how you can solve this module both fully by hand and with a little bit of computer assistance. That choice is obviously fully up to you. And hope this makes this module make a bit more sense. Thanks.